This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software. Thanks for your support.
This is Robert. I'm at the MongoSF conference with Dwight Merriman. Dwight is the CEO and co-founder of 10gen, the industry sponsor of the MongoDB open source database. Dwight, welcome back to Software Engineering Radio.
Thanks.
I say welcome back because Dwight was our guest earlier on episode 165, which is in the archives if you haven't listened to it, at which we were talking about MongoDB and NoSQL. Today, I will be talking with Dwight about database replication. Dwight, let's start out. Tell us, what is database replication?
Conceptually, it's very simple. It's just a replica, sort of as you think of in a dictionary, where you want to have a copy of the data on a separate machine. So, we're very used to replication on a single machine on multiple hard drives, i.e. RAID. So replication, sort of at the database level, is really to multiple machines. So I have a set of data and I want it on more than one machine, and I want it to automatically stay in sync.
Okay. What problem or what set of problems does replication solve?
Yeah, it solves a few problems. One is just data safety, right? So if I have the data on a couple machines, it's safer than if it's on one machine, right? So if it's on one machine and sprinklers go off on top of the server, you'd be apt to lose the data even if you had mirrored hard drives in the machine. So data safety is enhanced. In addition, you can use it to do disaster recovery. So if one of the replicas is in a different geography or data center, that's even better for data safety, right? If the data center burns down, I still have a copy of the data. It's also good for high availability. So, which is slightly different, right? Because my data could be safe if the machine just powers down and then later comes back up, but it's not available while it's down. So by having the data on multiple servers, we can increase availability of the data, which is important. And finally, I think people also use it as a way to scale. And replication is not a total solution for scaling. It's more of a solution in my mind to sort of high availability and data safety, but you can get some scalability of reads through replication to a point. I actually think that other techniques such as sharding or partitioning of data are probably a more generalized and solution to scaling than replication is.
Is replication also used if you want to transform the data on the replica for some purpose into a different form?
Sort of, yes. So I think you could just read it from the source and do the transformation and write it to somewhere else directly. But I think sometimes people they'll have a replica on which they do different tasks than they do on the primary. So they might do big batch jobs on the secondary and things like that. So that is one pattern that does come up.
Do you have different latency characteristics against the same workload?
Yes. So one thing people do is they'll replicate across geographies so that if you have a copy of the data close to the client, that's another reason to replicate.
You said replication is not a total solution for scaling. Could you elaborate on what you mean by that?
Sure. So first of all, in writes, replication doesn't help you scale writes, because if we're going to write, let's say, a new document to the database or a new record to the database, and we have, say, n replicas, basically we're going to do that write on every replica. right? So we didn't really gain any scalability because we're going to do the right n times. So it's really more useful for scaling reads, where if I have n machines, they all have a copy of the data, and each machine has a certain capacity, I should get n times that capacity in sort of reads per second by having the replicas. Now that said, there's some limits on how far you can scale up that way. One limit is just you have to do the writes at that many places. So if you had 100 replicas, it could be relatively inefficient to do every write 100 times. If writes were super, super rare, you might be okay. But if you had some, if you had one write for every 3 reads, it wouldn't make a lot of sense to write everything 100 times, right? Just so that you could get read scalability. In addition, that there's another issue, which is sort of cache affinity or lack thereof. So imagine we have 10 servers, and each server has 64 gig of RAM, right? So we've got 640 gig of RAM in the system, and that we replicate the same data to all 10 servers. And let's say the data is bigger than RAM. Let's say it's terabytes. So each server can process request, but what's going to happen is if there's a hot spot in the data, is all 10 servers are going to tend to cache the same most recently queried items, right? So I'm not really getting 640 gig of cache. I'm getting 64 gig of cache data, and all the machines are caching the same data. Now, if you're very astute as a client, you could say, well, I'm going to send requests for certain documents to this replica and certain documents to this replica, and then you're going to get some cache affinity, and then you're really going to get 640 gig of cached data. However, that requires a lot of a certain degree of sophistication and extra coding by the user. So that's a challenge too, whereas with something like sharding, you kind of get that cache affinity automatically.
How would you characterize a system where replication will be most effective versus, let's say, buying a bigger server and putting more memory on it?
As I think of it generally, I think of replication about safety and availability and things like that, and redundancy, and not so much scaling, right? So if I wanted to scale, I might use something like sharding and have several small servers instead of one giant server, right? And I think there's there's generally a sweet spot in server prices, right? So up to a certain size, the cost and the power of the machine scales up fairly linearly, and then beyond that, it gets very expensive to go bigger, or even impossible. So we really want to find that sweet spot, because if you can get a bigger machine cheaply, it's nice because then you have less machines to administer, right? But if you can't get it more cheaply, then I'd rather have more machines. So what that probably means is using a fairly large commodity server, right? So a server that's $5,000, $10,000, not using like a Sun server that's $100,000. That's not where your sweet spot is. So I'd rather have $10,000 commodity Xeon servers than one Sun server that's 100,000. And actually, if the scale up is not linear with cost, I should actually need less than 10. I should need maybe 4 or 5.
So I think your view is a little different than view that I think is more conventional in the industry, where if you're talking about applications where a lot of the data can fit in memory on a single node and reads outnumber writes, that replication is considered primarily a means for scaling out reads. Would you characterize your view as being slightly different than that, or do you mostly agree?
Yes, and I agree that people do use replication to scale. I'm just saying that it's not necessarily the optimal way to scale up. I think traditionally databases haven't scaled that well, right? They scale vertically, but not horizontally. So if you don't want to scale vertically, and the database doesn't have built-in support for scaling horizontally, what do? Well, you have a couple options. One is you could do replication, especially if you're read heavy, and then you have multiple machines to read from. So it's a valid tactic, but I think it's to some degree in that situation you're sort of working around the fact that the database isn't inherently horizontally scalable. The other thing you could do if you had a conventional database that didn't have that facility is you could manually shard or manually partition your data, in which case you wouldn't be using replication to scale. You would be using partitioning or sharding to scale, and you'd just be doing it yourself.
Is where you're going with this, that replication and sharding at some layer of the system are techniques that will help a system scale, but you would like those to be inside the boundary of what people call the database and hidden to some extent from the DBA?
Well, certainly hidden from the client user of the database. The DBA will probably have some awareness of how many nodes are in the cluster and what the replication factor is.
Let me ask my question a little differently. Is your view of what a data server should do is it should replicate and shard itself in order to scale by just adding nodes to the cluster?
Yes. And I think in some ways, databases have traditionally been able to do that with replication, maybe not completely transparently, but without any extreme effort. But the scale outside has been largely missing.
So let's talk a little bit about the backup use of replication as a backup solution. Could you go into a little more detail about where does that work best?
Yeah, so if you lose a machine and you lose all the data on the machine, if we have a replica, we still have the data. Now, of course, you could instead do backups, but the thing about backups is they're a point in time, right? So if I do a backup every 8 hours and I lose the machine, I lost the data from the last up to 8 hours. Whereas if you have replication, you've lost the data for perhaps 0 time or perhaps a few milliseconds. So depending on how you've configured. So in that sense, it's sort of like a continual hot backup, if you will, if you want to think of it in terms of data safety. So that's good. And these days, one does backups to hard drives anyway, not to tape. So it's sort of, conceptually, a replication is sort of like a rolling backup that's always there. One thing you do get into, though, then, is that if you sort of fat finger the system, right, like say you drop a collection or table, that's going to get replicated, right? So you lose it everywhere, no matter how many machines you had. So you do still probably want backups for that reason. In addition, any piece of software could have a bug, and maybe that percolates through all the replicas too. So that would be a good reason to have backup too. Also, in MongoDB, we have a feature we call slave delay, which means that a replica, you can force a replica to stay behind real time a desired amount. Like you could say, I want this replica to stay 8 hours behind real time or 4 hours behind real time. And it will sort of be a rolling backup from that far into the past. And that way, if you do have a situation where, say, you fat finger the system, you can go to the replica, which is slave delayed, and get the data back.
The difference between a backup and a replica then is there's a spectrum between them.
Yeah, I mean, a replica, as in the context here of data safety, a replica is basically a rolling backup. Now, there's other advantages of replication, such as HA, and also in some cases a little scaling up a bit. But in terms of data safety, it's effectively a rolling backup. It's also a backup that can be brought online quickly, right? Because with a conventional backup, you do the backup, the restore may take a while too, whereas the replica could very quickly take over, almost instantly.
I think we may get more into this later because I have some questions specifically about Mongo, but with Mongo, does it have the ability to identify when a write node has gone down and to bring one of the replicas online as a master?
It does. So in Mongo, the style of replication we do is sort of asynchronous master-slave or primary-secondary replication. To me, there's at least 3 flavors of replication one can do. The first is synchronous replication. So if you have 2 servers sitting side by side with a very high-speed connectivity network between them, or very low latency network between them, you could just do synchronous replication where you're effectively doing a distributed commit over those 2 nodes and servers. So they're always perfectly in sync. So that's been done with various databases in the past. However, we didn't want to do synchronous replication because we want MongoDB to work well on commodity hardware. We want it to work well in the cloud, right, where you may have some latency on the network. And we also wanted it to work well, the replication in Mongo, when you're replicating over a wide area network. So, in Mongo, if you have a database in California, you could easily replicate it over the internet or over your own network to, say, New York or Europe or Asia, and that would work just fine because the replication is asynchronous. And so, as I mentioned, we're doing what I would call asynchronous master-slave replication, which is pretty traditional. A product like MySQL can do that. There's another thing you could do, which is you can do asynchronous master-master replication, and some of the NoSQL products do that. That's when you get into more of eventual consistency semantics. We wanted to have some strong consistency and immediate consistency semantics available, so that's why we stuck to more of a primary-secondary approach. In Mongo, you can query the slave or secondaries if you say, I'm okay with eventually consistent reads, but writes always go to the primary.
So you mentioned the master-slave and master-master. Those are probably the two more common topologies. Talk a little more about some of the complexities with master-master topologies.
Right. Well, with master-master, really the problem would be conflicting writes. So
maybe you should just define master-master first, and then I'll ask you that question again.
Okay. So master-master replication, I would consider to be a system where you can write to any replica at any time. Would be a good example of that. And that means that writes will be arriving at different servers in the cluster concurrently on different machines. And in fact, maybe even when the network partitions, the different servers are receiving writes and processing them. So what can happen then is that you could have the same document on different servers being manipulated in different ways at the same time. And then what we're going to have to do later is somehow reconcile those manipulations of those documents, right? So if over here we have a document, and let's take an example of, let's say you're doing an e-commerce site and a shopping cart, right? And on one server, there's an add to cart for a given cart, and on another server, there's another add to cart, and on another server, there was a remove from cart, right? So we now have three versions of this cart object, and they're all different. And when we replicate asynchronously, and this data is going to flow back and forth, the question is, how do we reconcile those versions? And generally, what you would want to do there is you would want the kind of two add to carts to both show up in the cart, and the remove to go away from the cart. But the developer may have to write some custom version reconciliation code to make that happen, right? Because if we just use a strategy with this master-master replication of last write wins, that's not what we would want in this example, right? If the last operation was the second add to cart, we wouldn't want to throw away the other two operations on the cart.
There's some complexities in these master-master topologies that you don't have in master-slave, and there's no general solution to how you solve them in the master-master case.
Right. I mean, there's good patterns for how you address it, but I think in many cases they require some effort on the developer's part, and they also require care on the developer's part to not make mistakes, because in a lot of times in eventually a consistent system, 99% of the time it's immediately consistent. So it's possible that kind of in your testing that you're not really exercising the eventual consistency aspects of it, and then all of a sudden later, it passes all the QA, you get in production, that actually happens, then you would have a situation that you hadn't QA'd. So it would be important in those systems to be sure to actually test the eventual consistency in QA and staging by forcing a delay between the servers, or a partitioning between the servers in that environment before you get into production. So there are some nuances. Now, there are also some advantages. So eventual consistency makes it easier to do multi-data center configurations, for example. So there are pros and cons, but I think for the developer, there's a little more thinking and nuance when you go to those things. In addition, there are some problems that I think it's just not, there are some use cases where it's just not the right way to go. So for example, let's say you're building something like Twitter and you want people to sign up and specify a username, right? And they're either going to get the username when they register, or you're going to say, sorry, that name's already in use, give me another one. That's a situation where you need strong consistency semantics, right? Because we can't have two people allocated the same username at the same time on different servers and think they both have, the name Joe123. That would be bad, and so that would be very hard to solve, I think, with a pure, eventually consistent model.
You mentioned a few minutes ago that in a replicated system, there are situations where the programmer or the client has to pin a particular read to the master to get the level of consistency they need for that operation.
Right. So in MongoDB, by default, all reads and writes go to the primary. So you don't have to do anything special. You'll get kind of the semantics you would have expected in a traditional database by default. And then if you want to do reads from secondaries or slaves, you have to explicitly request that on your connection to the database and say, I'm okay with slave reads. Then the driver will use the secondaries in the cluster for reads and spread out the reads automatically. So by default, everything would go to the primary, so there's no surprises. And no matter which configuration you have chosen for a given connection to the database, the writes will always go to the primary because the primary is the only node that will accept the write in our model.
You've stated that the multi-mastery of eventual consistency, but isn't that also the case with a master-slave because of latency, that it's not fully consistent?
Yeah, that's a very good point. So it's the slave, if you're doing asynchronous replication, your slaves are eventually consistent. But if we don't do any failover, we could still have strong consistency semantics. So if you imagine using MySQL, you have a master and a slave, you can do the Twitter registration thing, right? Even though you do have a slave. It's just in the question of what am I using the slave for, right? If the slave is only doing reads of registrations, it's fine because when you're grabbing a username, that's only happening on the primary. Now the tricky part which comes in then is how do you do failover, right? So if you were using MySQL, you had or Oracle or something doing asynchronous replication, you have a master and a slave, and let's go back to our kind of Twitter style registration example, and the master goes down, right? Now maybe you want to cut over to the slave. Well, the challenge is that the slave might have been, because it's asynchronous, behind the master in terms of applying writes. Maybe it's 2 milliseconds behind or maybe longer, depending on the situation. But there is some window greater than 0 where it's probably behind. So the challenge is if you do cut over, maybe somebody registered Joe123 in those 2 milliseconds. And now you're at risk of it. It wasn't on the old slave that's now the primary. Somebody else could come in and register it again. Right, so this is a problem with failover in databases that we've had for a long time whenever we've done asynchronous replication. It's not a new problem, it's an old problem. If you were doing synchronous replication, you would be fine, but that has a lot of limitations. So this is a thing that we've thought about a lot, and we have a model that we like for it. So in MongoDB, there's this, we have a concept we call replica sets. And a replica set is a cluster of machines where any of the machines can be primary, any machines can be secondary. And with a shared nothing model, they will elect the primary, and then the others will be secondaries. And if the primary goes down, there will be automatic failover. There's also automatic recovery of a failed primary when it comes back up later. Now, then the question is, well, what about that latency because of asynchronous replication? So for our model, for if you have an important write, like the one we were talking about on the registration, what we allow the user to do is to request acknowledgement of the write only when the write has reached a majority of the members of the replica set, right? So in other words, I get my ACK back not when it's been written on the primary or master, but when it's made it to more than one node in the cluster. And it turns out with replica sets that if a write has made it to a majority of the members of the set, you're then guaranteed you'll never lose the write, because a primary will never be elected unless a majority of the set is up. So if you have 3 members of the set, i.e. you have a replication factor of 3, right? So we're going to have 3 total copies of the data. At any one point in time, 1 node will be primary and 2 will be secondary. If 1 node is down and 2 are up, we still have a majority, so we can elect a primary. If 2 nodes are down and 1 is up, we don't have a majority. So if we get acknowledgement from a majority of the members of a replica set, we know then we have a cluster-wide commit, and the data will never be lost, even though we're doing asynchronous replication. And that's sort of the model in MongoDB.
This approach you're describing to me, it sounds a lot like two-phase commit or synchronous replication. Would that be fair?
The write will occur immediately on the primary and then asynchronously to the slaves. It is a little bit like synchronous replication in that if you ask for an acknowledgement after reaches a majority of nodes, you're going to wait till it hits those other nodes. So in that sense, it's the same. But the interesting thing is you can kind of mix, right? So you may have some writes that aren't so important, and you just do them. You know they're going to percolate out, but maybe you don't care if you lose, the last 5 milliseconds of writes for that particular use case.
So your point is you can choose based on each instance of a write how appropriate it is for a given level of guaranteed of how secure that write is.
Right, and exactly. So, and you can also, I think it's just a little bit of a generalization because, I might have a cluster where some of the nodes are on a LAN locally, so you can get pretty fast acknowledgments, but maybe 1 or more are in a second data center for disaster recovery or something, and that acknowledgement is going to be slow. So if we waited for everyone to act, it could be quite slow, but if we waited for just the majority to act, maybe it's fast. So it's sort of that's a little bit of a hybrid, but we still do achieve, a cluster-wide commit in that situation. It's also a little different from synchronous in that we're doing basically read uncommitted read semantics. So if an item's been written to the primary, it may not have been written yet to the secondary. If you then read from the primary, you will see it, right? But if it hasn't made it to the secondaries and the primary crashes, it would be lost because the cluster-wide commit had not yet occurred, potentially. So, but you could read that. So unlike pure synchronous replication, you're getting read uncommitted read semantics, and I think in a lot of traditional databases you can request that, but it doesn't default to that. And so there's some pros and cons to that. So first of all, ideally you'd want read committed semantics, but that's the downside of this model. The upside is that we don't have a lot of locking going on and a lot of waiting going on for these other nodes to process the data, right? So if we wrote to a document and it needs to percolate out, if you have this read committed semantics, no one else could then query it until it had percolated out. So there's some pros and cons to this model, but in the real world, it works well for a number of problems.
You mentioned earlier that geographic redundancy is one of the use cases for replication. And did I understand that within a replica set, you can have nodes within different data centers belonging to the same MongoDB replica set? How would you size a cluster to be distributed across 2 data centers? Would you put half of the nodes in each one, or do you put one in the remote data center just as a failover?
Yeah, you could do either. So it's really up to the kind of system designer and the problem they're trying to solve. So one model would be to have a couple of servers in the primary data center, right? And then if one of those fails, the other one can take over, right? So it's sort of an HA scenario there. And then in addition, to have another member of the set that's in the DR data center, and that's really just for disaster recovery. So maybe you don't want to ever fail over to that node, but it's there for data safety purposes. So you can, in the replica set, configure a member and say, I never want this node to be primary, if you just want that behavior. You could also say, well, maybe it can be primary if everyone else is down, right? But in general, I don't want it to be because it's far away and it'll be slow to access.
You only have one master.
At a given time.
So that master is going to be in one data center.
Yes.
So if you're doing writes in the other data center, they have to go over the network to the remote location and then back.
Right. So the write would, correct.
And you talked about configuring nodes so that they can never be masters. Does a replica set have the ability to differentially configure each node based on what roles you'd like it to be nominated for?
Yes, it does have that capability, and in general, the preferred way to use it is to have as little special configuration as possible. That really just say, here are the members. They're all kind of peers. They can all do the same thing, and there's no single point of failure. They'll just elect a primary and do what they need to do. The upcoming releases of MongoDB will have some new support for data center awareness, so that it's easier to kind of get the behaviors you want. So for example, if you did say I'm okay with eventually consistent reads, it would then automatically talk to servers from the replica set that are nearby.
In general, when you have multiple read replicas and not necessarily limited to MongoDB, how do reads get distributed among the replicas?
Well, you could, I think the common case, if you are reading from the secondaries, would be that they could be round robin or randomly sent to any secondary, for example, or a connection from a client would be either on a round robin basis or randomly sent to a particular secondary, would be the way that that's balanced out. In addition, some users have a primary and a secondary. They do all operations against the primary. And the secondary is really there just kind of as a hot standby, hot backup, ready to take over if the primary fails. That's another way to use it. One thing to think about is if you imagine a system like, let's say we have two servers, right? So we have primary and a secondary. You could say, well, I think I'll send some reads to the secondary, right? Because that'll give me more capacity. But the only thing is, if you lose a node, and the other one takes over as primary, you only have one node up then. And the question would then be, well, can it handle the full load? Right, because we were using two servers to handle the full node. On the failover event, sort of, in this N+1 scenario, we're only going to use one server, and did we have enough capacity? Because our common case is both servers are up. Have we really measured that one server can handle the load? And if one server can handle the load, well, why did we even bother to send the reads to the other node anyway? So there are some nuances there and sort of capacity planning with, I think, any system where, you got to make sure that you have the right amount of capacity if you lose a server. And, if you have 100 servers, losing a server isn't a big deal. But if you have two, you lost a lot of capacity.
Capacity planning, you would want to think about how many servers do I have and how many could I lose?
Right, and a lot of people talk about N+1, where if I need N servers to run, I have N+1 servers so I can lose one. And if you have a very large number of machines, you would want to have more than one extra server, because with a lot of machines, there's a significant probability of losing more than one at the same time.
I want to get a little bit under the hood on how replication works. Is it more common that the master is pushing updates out to the replicas, or are the replicas connecting to the master and pulling the updates from the master?
So in MongoDB, the model is that the secondaries will pull data from the master at whatever rate they can take it. And so they'll kind of, there's this concept in the database of an op log or an operation log, which is really a log of all writes which have occurred. And that's sort of like a circular queue of writes which are occurring on the primary. The secondaries will then basically tail that queue and apply those items locally. And hopefully they're keeping up and they're applying them almost immediately. But if they weren't keeping up, or maybe they were down either for planned maintenance or unplanned, they'll catch up when they come back online. as long as the op log was big enough that it goes back far enough in time that they can sync back up.
Does the replication impose any significant load on the master?
Yeah, that's interesting. Not very much, surprisingly, right? So we're writing to this op log, but the writes to that op log are sequential writes. So there's a little bit of overhead there. And then the secondaries are querying this data from the primary, right? From the op log. But they're really just tailing the end of the op log, right? So they're really just hitting data that's in RAM, and they're pulling it sort of kind of sequential off the tail of the collection, of the op log collection. So it's actually pretty efficient. So it turns out in practice that the overhead is actually fairly low.
Is there any number of replicas where the overhead would start to be significant? Or is that not really the limiting factor in how many replicas you would have?
Well, it would be significant probably if you had 10 replicas, let's say, in a replica set. But even then, it's not too bad because they're all going to be telling the same op log. They're all going to be, say, give me the end of the op log, which is in RAM. So I need to shoot it out to all of them, but it's pretty easy because they're all asking for the same thing. It's in RAM. And I'm still only writing it once on the primary to the op log, no matter how many there are. So it actually scales up pretty well. I mean, I think the limiting factor is really just that there isn't a great reason to have a lot of replicas, right? You know, you might want more than 2, let's say 3, just to have more data safety and higher availability, so you could potentially lose more than one machine. You know, you could imagine having 5 copies, maybe if you're doing a lot of reads from secondaries. But generally, it would be unusual to go higher than that, even though you can.
Are the replicas polling the master then?
Yes, they're basically tailing the op log on the primary. And in a replica set, you have automatic failover and recovery from failures in the set. So what will happen is there will be this continual polling of each member in the set of the other members. And they will then notice if a node is down, in particular if the primary is down. And if everyone is seeing that the primary is down, there will be a new election. So if a majority of nodes think that the old primary is down, they will elect one of themselves as the new primary and take over.
And how does that election process work?
It's just a peer-to-peer kind of consensus election protocol. What we did is pretty simple. It would be a little bit like a Paxos algorithm, but we're actually doing something a little simpler and slightly less efficient because the elections are infrequent. So it's not necessary really to make it perfectly optimal. It's just got to be correct.
What would happen if the former master came back online and found it was no longer the master?
Exactly. That's a great question. So imagine, let's take the example again of a traditional database like MySQL, and we have a master and a slave, right? Let's say the master went down, right? And that we cut over to the slave and we promoted it to be a master, right? Then we do a bunch of writes to it. Now let's say our old master, we fix whatever was wrong there and we bring it back up and we'd like to get it back online. Well, the challenge is there was probably, because the replication was asynchronous, there was probably a few writes that hit the old master before the new one took over. So it's in an inconsistent state.
This is the multi-master problem all over again.
Right. So there's then 2 options. One option is the DBA could say, you know, those few writes in that little interval there, I don't really need them. So what I'm going to do is I'm just going to make the old master be consistent with the new master state. Now, unfortunately, to do that would probably means with a traditional database, you need to do a full image copy back to the old master, which is not ideal. The other thing you could do is you could manually, as the DBA, try to merge the data yourself. So you can do that, but you need to, you could imagine that taking like a full day to do. And given with MongoDB, we want to be able to build large clusters with, say, 1,000 machines. You know, machines are going to be failing and coming back up all the time. So we need a solution that's completely automated, that doesn't require a bunch of DBA effort on the failover and recovery. So that's why we've got the replica set model. So you have those two options, so kind of full image copy from the new master or manual DBA merging traditionally. So what we did with replica sets is we basically did something analogous to the first scenario, which is to say I'm just going to drop the data for those few milliseconds that was sort of lag, and if that was important, you should have asked for acknowledgement from majority, and you can. And then the question is just how do we quickly get that old master back up, right? We don't want to do a full image copy. So what we actually do is when that node comes up, it'll see the other nodes, and it'll say, hey, I'm out of sync. You know, I'm coming back up. There's been a failover. There's been other writes elsewhere. The old primary will then roll back the operations it had written in that small interval of time that never made it out the door, making it then consistent with a previous point in time from the rest of the cluster, and then it will, as a secondary, start applying items that were written while it was down and getting back caught up. So you can very, very quickly have a server recover in a MongoDB replica set and get back up and in sync with very little effort, which is nice.
How could you characterize the size of the op log, either in terms of so many minutes of data or bytes of data?
The size of the op log you need depends on how fast you're writing, right? So let's say you want a secondary to be able to be down for an hour, right? And then be able to come back up and catch up. So we then need to have an op log that will store at least an hour's worth of writes, right? So if you're writing very little, your op log probably doesn't need to be very big to store an hour's worth of writes. If you're writing massive amounts of data, though, you could have written a giant amount of data in an hour. And maybe you want more than an hour. Maybe you want 3 days, right? Maybe you want, if a server's down for 8 hours or 24 hours, that it can sync back up. So generally you want a pretty big op log. And in terms of disk, in terms of space on disk drives, disk is cheap, right? So our general thinking is make the op log very big. From a storage perspective, disk is cheap. From an IOs per second perspective, disk is expensive, right? So the thing we need here is space, not IOs per second. So we would recommend using a large allocation for the op log. And in fact, I believe the default op log size, if you do not request a particular size, is about 5% of the total data volume size. So if you had a terabyte drive, we'd actually take 50 gigabytes for the op log by default.
What you're trying to save by having a bigger op log is the situation where you have to rebuild a full image of the database.
Right. So imagine I have a terabyte data drive, right, or data volume. If I'm too stale to catch up, I then need to copy everything over, which in this case would mean copying over a terabyte of information, right? So we wouldn't want to do that. So we'd like to catch up from the op log if we could. I'd rather pull over 50 gigabytes than a terabyte, and that would be much nicer.
Does the op log contain the statements that were applied to the database, or is it some more compact form that can be written directly into the disk?
The op log contains the logical writes that basically happened on the primary, and so it's not necessarily a more compact format, but in some cases it is pretty compact. So if you inserted a new document, the whole document would appear in the op log. But if you did a partial update to a document in MongoDB, like let's say you just set one field, the actual $ set of one field is what will be in op log, which is quite small. So you may have a very large, let's say you have a document, it's 300 kilobytes, one document. If I just increment an integer in it, then the data in the op log for that increment will be quite small. And an important point there is, which I think I already said implicitly, is that the op log for replication is at a logical level rather than at a low-level physical level. Because there's two ways you could do replication. First, you could store in a transaction log or redo log, if you will, high-level write operations to the database, Or you could store very low-level physical writes to the data files. You could say, okay, this file, this offset, this length, these bytes, right? So that's one style. It's sort of this low-level writing of, the actual file IOs. And then the other style is very high-level, insert this document in this collection, and without specifying anything further. So in Mongo, we're doing the high-level logical version. And we like that because that means that the primary and the secondaries don't have to actually have the data in exactly the same physical file locations. So for example, if you wanted to do a compaction or repair of a copy of the database on one server or the other, that will then, if you did a compaction, things moved around. The system's not going to mind then when you afterwards, because at the logical level they still have the same data. In addition, let's say you upgraded to a new version of one of the nodes. The system will generally be okay with the fact that server 1 has one version and server 2 has another version, and if they don't actually store the data exactly the same way on disk, that's okay. If you do the low-level logging, what you typically have to do if you do a system upgrade is you have to upgrade all of the nodes in the cluster at the same time, and you can't run mixed versions. So doing it at the logical level, we can support that.
Talked earlier about partitioning data, sharding data in order to get scalability. Would you then not want to replicate each shard for reason of backup or availability of each shard?
Definitely. So in Mongo, the way we think about the problem is we think of replication and sharding as being orthogonal. So we think of replication as really being about data safety and HA, and as sharding as being the way to scale up, right? So sharding is basically partitioning. It's order-preserving partitioning. So if you're sharded on a particular key, keys that are close together in the key range will tend to be on the same server, which has some nice properties. But basically, we're partitioning. So a given document in the database will be on one and only one shard, right? So it's partitioning, right? Every shard has different data. With replication, it's exactly the opposite. We want the replicas to be identical, right? So what happens with Mongo is you'll have some number of shards, and then for each shard, you'll typically have a replica set within that shard. So if a machine within that shard's replica set fails, there's failover available.
If people would like to find out more about MongoDB, how can they do that?
Go to the website, so mongodb.org. There's a ton of docs there, and there's also presentations, including video presentations on replication, sharding, intro to Mongo, things like that. Or just jump into IRC or the forums and ask a question.
If people would like to find out about 10gen, what's the best way?
10gen is a company that's commercializing MongoDB. We began the project, but it's an open source project now. So if you want to use it for free, it's highly encouraged. Go to mongodb.org and do that. If you want some commercial support and services, go to tengen.com and we can help you there for sort of enterprise, 24/7 production support and advisory consulting and things like that.
Do you blog or tweet, or how can people follow your thoughts?
Yeah, so there's a MongoDB blog, which you'll find from the site, and MongoDB is the Twitter handle for Mongo, and then I think mine is DMERR.
And I'll also recommend, if a Mongo event comes to your city, I've been to the last one in San Francisco, and they're very, very good events. So that wraps things up. Thank you for talking to Software Engineering Radio.
Thanks.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To support us, you can advertise SE Radio by clicking the Dig, Reddit, Delicious, or /dot buttons on the site, or by talking about us on Facebook, Twitter, or your own blog. If you have feedback specific to an episode, please use the commenting feature on the site so that other listeners can respond to your comments as well. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Please see the website for details. Thanks again for your support.